Click continue. I log into the class myself. If you see one of the students in the class is named Monitor, that's my cell phone. Just so I can be sure that I'm seeing what you're seeing, because I hate it when I lecture for a few minutes and I'm meaning to be pointing at a slide or showing you something. And then I discover, because somebody will say, Professor, if you're trying to show us a picture, we're not seeing it. And this makes me crazy. So I'm seeing what you're seeing on my phone here. So I guess nominally I'm calling this week 10. I don't really know what it is in the course of the semester, but we'll call it week 10. You can always hop around to any of the other weeks. If you have missed a quiz, if you know 1 week you were just behind and you never took that quiz, I have the quizzes set such that they don't close. So you can go back and take a quiz if you missed it. You may also, if you never did your second attempt at a quiz, it's not too late. You can go back and do that. I was talking to a person who has fallen behind, and I gotta tell you, my life is full of this. I have my son, my older son is a senior at Salem State, and he on occasion falls desperately behind, and he feels anxious about it. And it's this horrible cycle where he's behind and he doesn't feel like he can re-engage in the class until he catches up, but he has such anxiety about trying to currently participate in a class if he's 3 weeks behind in the material. And I appreciate what that looks like. I appreciate what harm it can do to you. So please, if you're here and listening and behind in any way, please know that you can catch up. It is okay. You can take the exam, you can take the quizzes, you can do whatever it is to catch up. It is my best advice to you to be engaged in class right now, because we're going to be talking about chapter 7, and we have a quiz on chapter 7 next week. And so it's important that you engage in that. It will be important that you try to make an attempt at all of the chapter 6 homework before Friday when we have a quiz on chapter 6. It's really important that you keep current as much as possible. And then if you can, while you're doing the chapter 6 stuff, go back and do the stuff from chapter 2 as well. Maybe you can handle 2 weeks of things in a single week if you're in catch-up mode. But it would be horrible and impossible for you to go back and do chapter 2, 3, 4, 5, and then 6 to be able to take, like, that's just too much on your plate all at once. So keep current, and this is for this class and any other class you're in. If you've missed class, if you've missed 2 weeks of class, get back in there and keep up with what's going on right now, and then try your best to catch up on the stuff from the past. And I can only speak for me, but you can take the exam. If you somehow got behind and didn't take the exam, you can still take the exam. If you've missed any quizzes, you can do the quizzes. The homeworks are all open. Look at your homework grade. If it's not 100%, you can do something about that, because you can keep doing the homework until you have a perfect score on each homework problem. The point is learning the material. I'm not trying to arbitrarily punish you for falling behind or getting a little disorganized, or just, you know, being in the insanity that we're all in COVID days. So let's work together and get us all through this. I want you to succeed. I want you to get this class behind you and get into the next class and make your way toward graduation and a fantastic career in whatever it is you want to do. I'm trying to help. But I will also point out, I walked out of the house today to walk the dog while my wife was on the phone with somebody doing a recommendation for one of her students, and one of her students who graduated, one of my students too, who graduated last year, 2 years ago, and is applying for a different job. And there's stuff that your future employers want you to know, want you to understand, skills they want you to have developed while you're in undergrad. And so I can't just, give out grades like candy, because that, ultimately harms you. You need to learn the material, and to learn the material, you need to engage in the material. I'm trying to make it as low threshold, as low hanging fruit as possible to, just take a whack at the homework. If you missed the chapter 6 lecture, if you don't understand chapter 6 at all, click on that first chapter 6 homework problem and try to do it. And then watch the video if you don't understand what's going on in the problem, and then open up the link to the textbook if you need a little more background information. There's ways that you can build up to, what is it I know, what is it I don't know, and get yourself to the place you need to be. Sorry, the oven's warming up. Gonna make some lunch a little bit later. Okay, so enough blah, 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 general life skills. This lecture isn't a long one, so maybe it's all fine that I took a little extra time to blah, blah. Let me find the lecture. It's got to be here somewhere. Okay, new share. Come on, new share. So chapter 7, we're into the world of work and energy. This is, I kind of want to say there's nothing new. We have built up in physics so far. We did kinematics, just motion of objects, velocity and acceleration and displacement. And then we introduced mass in kilograms as a new concept. You had motion, but then once you have mass in kilograms, that changes the game a little bit, because it's a very different thing if a 50 kilogram ball is rolling toward you, or a I don't know, 2,000 kilogram truck is rolling toward you. There's different experiences there. So mass, force, that was a new concept, and there was a lot of stuff around there. We then got into the world of uniform circular motion. That's the chapter 6. And it's not really a new concept. It's something moving, but it's moving in a circle. Okay, I get that now. And there's a force associated, centripetal force, and there's velocity and time, and a lot of the same ingredients that we had before. We're going to use a lot of the same ingredients, but we're going to look at them in a new way to talk about this concept of work and energy. And I used to make this joke that I thought was funny about how Taco Bell has 3 ingredients, and they put them in different arrangements in all of their products and call it something different. I don't know if that's funny or not, but when we deal with work, energy, kinetic energy, everything is the same basic ingredients: kilograms, meters, seconds squared, and we put them together and we call that joules. but it looks different. One of them looks like a taco and another one looks like a chalupa, and but it's the same thing kind of built into it. We just experience them differently. So what's going on? So what is work? I may have regaled you with the story of the sociology major, I think he was, who took physics, and every day after class, he would come up to me and try to relate the concepts of physics to the concepts of like social movements. And it was really interesting to have those conversations. So here, when we talk about work, most people have some idea of what it means. You know, I'm going to go to work. Oh boy, that was a lot of work. That was a workout. You know, there's different ideas that we have. So in physics land, we're going to have kind of a unique definition of work. So it's not going to be the amount of effort required to do something. Maybe that's how we typically think about work. But we're going to do, and I apologize for the wording here. I got to be really careful with this. Saying the application of a force over some distance, but that's not divided by over, that's like through some distance. So if your car breaks down and you push it down the road and you're applying a force in the positive x-axis, a force of 100 newtons, and you push your car for a distance of 30 meters, we would call that you did work. The work done on an object, so on the car, by a constant force coming from me is the product, multiplying, of the magnitude of the displacement, 30-meter distance, times the force of, I mean, I don't know what's normal, 100 newtons. So 100 times 30 would be like 3,000. I did 3,000 works. Well, it'd be 3,000 joules of work. The product of force times distance is going to be units of joules. The cosine theta piece is the angle between the force and the displacement. And there's nothing inherently x-axis or y-axis with this theta. So right now, if I'm pushing my car down the road, my force is in the positive x-axis. The displacement of my car is in the positive x-axis, but who cares? The important thing is that there is no angle. The angle between my force and displacement is 0 degrees because they are both in the exact same direction. Cosine of 0 degrees, and we're always keeping our calculators in degrees, not radians, even though we talk about radians in chapter 6, and we will again, but even though we talk about radians, we're not changing our calculator, not changing our trig functions to radians. We're keeping that in degrees always. Cosine of 0 degrees is 1. So for this kind of example, when your force and displacement are aligned in the same axis, it is simply a multiplying force times distance, and the unit is joules. So work equals force times displacement. Force equals mass times acceleration. So mass times acceleration times displacement. Acceleration is change in velocity over the change in time. So what the triangle means, delta, change in. Velocity is change in displacement over change in time. So what the heck are the units here? If it's just force and displacement, that would be newtons times meters. If it's force as kilograms times meters per second squared times meters, or do we multiply meters through and call that kilograms times meters squared per second squared? It is one of the realities of your existence when you teach, that you say the same things over and over again, but you don't necessarily remember who you said them to. So when I have geological science majors take physics, oftentimes those individual human beings, whatever it is they do in their department, they are amazing at keeping track of units, and they can hammer through almost any problem just by keeping track of the units. And so all of these units that we see right here all are the same thing. It's joules, joules of energy. And wait until you take physics 2, and suddenly we're using joules to describe thermal energy, heat energy, and electric energy, and everything is related. It's amazing. But right now, we're starting, with simple basic steps. If I, whatever, if I lift something up and the thing weighs, weight is in newtons. So if it has a mass of 5 kilograms, it has a weight of 49 newtons. And then I lift it up 1 meter of distance. So I've done the weight force times the distance that I lifted it. I did 49 joules of work by lifting something up. We will save the guy on the thing for a little bit. All right. This was a question in an earlier textbook. If you didn't have the same childhood that I had, then maybe you're not aware that a toboggan is a type of sled. So it's a sled that slides along the snowy ground. And if there's snow, then maybe there isn't a whole lot of friction. I guess it doesn't particularly matter whether there is friction or not in this question, because we have a person pulling a toboggan, which is a sled on the snow. I gotta find my place. So toboggan, somebody's sitting on the toboggan. There's a person here pulling the toboggan. And so it's going to travel a distance of 35 meters. The person is pulling with a force which is revealed in the tension in the rope. The funny thing there is sometimes physics gets really specific about the forces, and the person who's pulling the sled ultimately, this person isn't touching the sled. They're touching a rope that is tied to the sled. So they're pulling on the rope, and it's the tension in the rope that's pulling on the sled. That can have a significant difference if the rope will snap if you apply too much of a force. So we're transmitting the force from the person to the sled by way of a rope. And so we talk about the tension force in the rope. And this is angled at 25 degrees above the snow. So that gives us the case where work equals F d cosine theta. We do have an angle theta of 25 degrees. So 94 newtons of force. Sorry that my 4 looks like a 9. That happens all the time. 94 newtons times the distance of 35 meters times cosine of 25 degrees. And so, wake up calculator, 25 cosine times 35 times 94 is 2,982. 2,982 joules. There are times when you're doing physics problems where I hope an alarm goes off in your head when you see a number and you're like, wait, that can't be right. So if you're doing something with, you know, the weight of a rock and you come up with a, you know, answer of 1 times 10 to the negative 9th, you should probably say, wait a second, that doesn't seem like a normal magnitude answer for the weight of a rock. A rock probably weighs something in the 1s to 10s of kilograms, and then you multiply by 9.8, we're in the 10s to 100s of newtons. Like that, hopefully you build up some kind of instinct like that. So when you see bizarre numbers, a little alarm goes off. When you're doing things with work and energy, thousands is a really common kind of answer. So when you see answers in the thousands, don't think, whoa, that seems awfully large, because it might not be. That's a reasonable answer for a certain amount of work. How much work is done if the same tension is directed parallel to the snow? So I guess in the second case, we're like leaning way back and pulling, you know, directly parallel. So in that case, work equals FD cosine of 0 degrees, which is 1. So it's just going to be the 94 newtons times the 35 meters. 94 times 35 equals 3,290 joules. And I guess the point to make there is that in this instance, when we're pulling at an angle of 25 degrees, some of our pulling force is up in the y-axis, but the sled's not moving in the y-axis. Therefore, any force that is directed in a direction other than how the thing is moving isn't doing work. It's doing something maybe, but it's not actually contributing to the work. So we need a more robust definition of what's going on here, because there's 2 different things happening here, right? One time the person's pulling up at an angle and they're only doing 2,982 joules. The other time they're pulling exactly parallel. Now they're doing 3,290 joules of work. What does that look like? What's the difference? What's going on when you do work on something? Clear all drawings, close the UBI, and move on. All right.
I have a quick question,
so,
I'm sorry.
Yeah, go ahead.
I actually would have thought that the work would have been less parallel, because you're not pulling up, which is not in the direction of the movement. So therefore you're not wasting that energy. So I would think you could like conserve energy by pulling on a more horizontal. But obviously I'm wrong, so.
So the steeper the angle, so that was 25 degrees. If we did 40 degrees, if we did 60, if we did 90 degrees, you would be simply lifting the sled up, and maybe it would move in the y-axis up, and that would be a totally different scenario. But if you're just pulling the sled up, but it's not moving up, you're not doing any work. So we're leading into this idea of work as a vector quantity, because work, it matters the direction and the motion, the way the thing moves. So my little example here, you know, can one do positive work? Can one do negative work? Is work a vector quantity? And so if you're working out at the gym, I am given to believe that if you are lifting free weights at the gym, it is a bad idea to lift up the weight over above your neck and then just let go, because the weight will come crashing down on your neck and cause you some harm. So if you're working out with free weights, you would apply a force in the positive y-axis as you lift it up, but you will also apply a force in the positive y-axis as you allow it to move back down again. Either way, your muscles are doing work. But in one case, the force and the displacement are both directed upward. So I guess we're calling that positive work. And in the other case, the force is up, but the direction is down. Is that negative work? And it is. So the big reveal here is, what does it mean when we do work on what is done to the thing? And so with the sled, when you do work on it by pulling it, the work is probably going to reveal itself in a change in kinetic energy of the sled. So if you're pulling, part of your force is up, part of your force is over, so there's less force in the x-axis, the sled's not going to be accelerating as much, not going to have as big a velocity. But if you're pulling purely horizontally and leaning into it with the same total force, you will get that thing moving faster. Here for the weight, the difference is, and here we get bum, 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 the work energy theorem. It's the relationship between work and energy. So we should talk about what energy is. And I kind of gave you a preview of your future physics career, where energy might be heat energy, thermal energy. Energy might be electric energy, the energy that comes out of a battery that's running your phone or your laptop or something else. Those are forms of energy, and we will build into those in the fullness of time. But for right now, energy is going to be either kinetic energy. Kinetic energy is the energy of motion. Anything that exists has mass, and anything with mass that is moving has velocity. And so velocity squared 1/2 mv squared. This is one of those equations that a lot of people would have heard of before they got to physics class. So for whatever reason in the world, a lot of people know force equals ma. A lot of people know kinetic energy equals 1/2 mv squared. And then however impractical it is, most people know E equals mc squared. So we have like 3 physics equations in the bank already before we even show up to class. And 2 of them are pretty practical for our work here. So kinetic energy, the energy of motion.
Professor,
Anything that exists has mass. Anything with mass that's moving has kinetic energy. Is there a question?
yeah, I had a theory on the E equals MC squared thing. I think it's just because it's such a huge pop culture thing. Everybody knows it.
Yeah, I think so. I mean, it's just kind of funny because we won't get to it in the course of introductory physics 1 and 2. You'll have to keep going in your physics career before you're going to start converting matter into energy or vice versa. So it's just kind of funny how it's such a pop culture thing.
I think it's with the nerds. They just see E equals MC squared. It's like, oh, Eureka! Or something like that. I don't know.
So work has units of joules. Talked about that. Kinetic energy has units of joules. And then the other type of energy is, oh, can I flip? No, I can't. I gotta close it. Then go to the next thing. The other one we're calling gravitational potential energy. Gravitational potential energy is much like the name sounds like it. If you lift something up, it has a certain amount of potential energy. If I pick up a 1 kilogram mass, 1 meter off the floor, so M is 1 kilogram, G is 9.8 meters per second squared. So 1 times 9.8 is 9.8 newtons of force I had to apply over a distance of 1 meter. I'm like lifting up my hand off the screen as though that helps you imagine me lifting up a mass. I can't explain myself. But if I take a mass and I lift it up 1 meter, I'm mostly on the screen here with my imaginary mass. It then has the potential to do something. I did work lifting it. This GPE is work, right? Force times distance. I did work lifting it up. Now it has potential energy. And if I let it go, it will fall back down to the ground. That potential energy will turn back into kinetic energy, or will turn into kinetic energy. So there's 3 different things here. There's the work that I do. There's the potential energy that is stored for some amount of time. And then there's kinetic energy, the instant before it hits the floor or hits my foot or whatever it does, the instant before it comes crashing down to the ground again. It has a certain amount of velocity, it has mass, and so that we call that kinetic energy.
I have a question.
Yeah.
Is there such a thing as static energy? Or like or is it like, am I just kind of making something up?
If you were
Like static
taking,
force kind of being the same as gravitational potential energy, not really, no correlation.
there's stored energy, and we'll get a little bit deeper into this in a little bit, where you can store energy in kind of a compressed spring. So that would be elastic potential energy. But if you're playing pinball somewhere and you pull the plunger back, right then that is stored elastic potential energy, which will be released into making the ball move. So you could call that a static kind of energy. In the world of physics, like if you were doing engineering physics somewhere, you would do entire courses on statics. And statics are any situation where something isn't moving and there can be a whole bunch of forces acting on it, but they're all canceling out so it stays still. So I don't know that they would refer to anything in there as static energy.
Okay, I'm sorry. I was just.
No worries. And there's certainly electrostatics, and that we do in physics too. I'm teaching physics 1 by day and physics 2 by night. And we spent our time on electrostatics, and we are on the cusp of having electric circuits going in the physics 2 night class. And there's all sorts of fun there. If I was a better person, I would have set up a poll to get your answers on this one, and I did not. I'm sorry. So at the bowling alley, so this is a what's a concept question. So there's numbers, but it's meant to be fairly easy to do in your head, such that it's almost kind of a conceptual question, what's going on. So at the bowling alley, the ball feeder mechanism must exert a force to push the bowling balls up a 1 meter long ramp. Now the ramp is 1 meter long, but ultimately it's taking it up to a height of 0.5 meters. The ramp leads the balls to a chute that is 0.5 meters above the base of the ramp. Approximately how much force must be exerted on a 5-kilogram bowling ball in order to get it to roll up this ramp? So because of the work energy theorem, the work that we do equals the gravitational potential energy that the ball gains. So the work is force times distance, and the gravitational potential energy is mgh. So on these kind of questions, they get cutesy and they just call the acceleration due to gravity 10 meters per second squared instead of 9.8 because it makes the math quicker and easier such that you can do it in your head. So 5 kilograms times 9.8 times 10, sorry, 5 times 10 is 50 times a height of 0.5 meters would be 25, sorry, 25 joules of gravitational potential energy at the top of the ramp. Therefore, the force is going to be 25 joules divided by the 1 meter long ramp, 25 newtons of work. The angle on that, work equals FD cosine theta. The angle is 0 because the force and the displacement on the ramp are both in the same direction. Doesn't matter x-axis, y-axis, or even some angle relative to the ground. All that matters is the angle between the force and the displacement. So, 25 newtons of force in order to get the ball. Now the ball's going to be gaining gravitational potential energy as it goes from floor level to the top of the ramp. So it's gaining 25 joules of gravitational potential energy. But in order to give it that many joules of gravitational potential energy, we had to exert a force of 25 newtons. All right. Clear all drawings. 2 marbles, one twice as heavy as the other, are dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has as much kinetic energy as the lighter one, twice as much kinetic energy, half as much kinetic energy, 4 times as much kinetic energy, or it's impossible to determine. So I don't want to be sad, so I will point out that if you drop things from the top of a building, a big thing and a little thing, they will hit the ground. Sorry that my lines aren't really perpendicular to the ground. At the same velocity. We're ignoring air resistance when we do this, and the acceleration due to gravity acts on heavy objects and light objects just the same. So the 2 marbles that we're dropping from the roof of a building will hit the ground with the same velocity. But presumably, as intelligent human beings, if we had to get hit on the head with one of these marbles, we would rather it be the lighter one. Why does it matter if they're moving at the same velocity? Well, it matters because they have different amounts of kinetic energy when they hit us in the head. Kinetic energy, 1/2 mv squared. So the heavier marble, which is twice as heavy as the other one, will have twice as much kinetic energy as the lighter marble. Funny things in my teaching career, I inserted my young son as liking answer number 2, and he has in fact taken this course with me. He's much older now, but he is still very much just as orange. Kids come out different. Some of them apparently come out orange.
Did he point it out to you when he first saw that? He was like, "Oh, that looks like me as a kid."
When I think I showed it to him when I first inserted it into a lecture. I don't even know the occasion that I took this photograph. And then when I was about to click on the slide during lecture, I'm like, oh no, he's gonna be upset. Because there's no truth to the generalization that redheads have short tempers, but maybe there is. So we have a water slide here. This is a difficult question because it's tricky. There's pieces to this that you would have to pick out to be able to get to the answer. The general strategy with a water slide question is at the top of the slide, and we got to compare to where the guy leaves the slide. The top of the slide, it's all gravitational potential energy. And then at the bottom, it's kinetic energy. So that's kind of the easy part. The gravitational potential energy turns into kinetic energy. Now the kinetic energy at the bottom of the slide, we're given this bit of information that the person leaves the slide traveling horizontal. Oh, I wish I could do better angles, I'm sorry. Leaves the slide traveling horizontally and travels for a distance of 5 meters before they hit the water. And they do that in a time of 0.5 seconds. So their velocity at the bottom of the slide, velocity at the bottom, it's a B for bottom, is going to be, they're traveling 5 meters in 0.5 seconds. So that is 10 meters per second. So from the top of the slide to the bottom of the slide, they have mgh turns into 1/2 mv squared. Now it turns out that mass appears on both sides of this equation. So they never told us the mass of this person, but it turns out it didn't matter because it cancels out. So GH equals 1/2 V squared. V was 10 meters per second. So 1/2 times 10 meters per second squared times 100, so 50. GH equals 50 meters. The total height from the bottom of the slide to the top of the slide is going to be 50 meters divided by 9.8. I'm sorry, not 50 meters, 50 meters squared per second squared. 9.8 meters per second squared. The height is 50 divided by 9.8, 5.10 meters from the top of the slide to the bottom of the slide. The extra kicker on this problem is from here down to water level took place in 0.5 seconds of free fall motion. So what do we know? We know time. We want to find distance. We know acceleration. We know that the initial velocity in the y-axis was 0. So v equals, I don't know the final velocity. I want to find the distance. Where are my equations of kinematics? Y equals v naught t plus 1/2 at squared. So the y-axis distance, the initial velocity in the y-axis at the bottom of the slide where they launched horizontally is 0. So y equals 1/2 times negative 9.8 meters per second squared times 0.5 seconds squared. It's a very tricky problem. 0.5 squared times 9.8 times 0.5. Oh, come on. 0.5 seconds squared times 9.8 divided by 2, 1.225 meters, negative 1.2 meters. So this distance down was 1.2 meters. This distance from the top to the launch point was 5.1 meters. So 6.3 meters total H. I may have you answer questions where you do the top of the slide to the bottom of the slide, converting gravitational potential energy to kinetic energy, but I probably wouldn't do something as mean as this whole problem. But sometimes it can be helpful to see a more complex thing and then approach it as a simpler thing. All right, so take a quick peek. That was my simplified version of the thing. If we were in lab, you would walk and run up a flight of stairs and talk about the work that you did. When you go up a flight of stairs, it's the difference in your gravitational potential energy at the bottom and at the top. So there's all sorts of ways that work and energy take place. I would also do this example. I didn't do this example. If we were in a lecture hall, I would pick up a chair. Very impressive. I'd pick up a chair and say, oh, I did so much work lifting up this chair. I applied a force in the positive y-axis and it moved in the positive y-axis. I did work that is now equal to mgh, the gravitational potential energy of this chair that I lifted up off the floor. And then I would walk across the room with it. And suddenly I'm exerting all kinds of effort. It takes effort from me to hold the chair up a meter off the floor. But according to our physics definition, I am no longer doing work. I'm not increasing the gravitational potential energy of it. And that our work equals FD cosine theta. If cosine theta is if theta is 90 degrees, cosine of theta is 0. I'm not doing any work carrying it horizontally. It's a frustrating, obnoxious thing about physics that we just have to deal with. These are just images from the book. I don't think there's particularly anything else. What I like to do is take a peek at our Canvas page. And look at the homework problems for chapter 7. To see if there's anything that I didn't talk about. And there is a thing I didn't talk about, which is Hooke's law, which has to deal with springs and spring constants. But we will take a little bit of time before the quiz on Friday. We'll talk about Hooke's law, and we will talk about power. We've talked about work and energy, but there's one last piece to the puzzle that we have to talk about, and that is power. So Hooke's law and power on Friday. And then I'll field any questions you have before the quiz on chapter 6 material. Sometimes I copy that stuff over and I didn't this time. So our week 9 was where we covered chapter 6. So you can go back and click on that week and you see all the videos for the chapter 6 homework problems. We'll go over these on Friday before you take a quiz. But that is enough for today. I will post the recording when it's done, but you are free to go. I will see you on Friday. Have a happy day.
Thank you.
You're welcome.
Thank you. See you Friday.
Thank you, Professor.
You're welcome.
See you Friday.
See you.
Thank you.
You're
Sorry,
welcome.
I just said love you because I'm instinctively saying love you to people because I'm so used to hanging out with my family.